Section 1 Introduction. We're going to talk about how large language models, or LLMs, have revolutionized the field of natural language processing. These models have exhibited significant advancements in understanding and generating language, with special abilities such as zero-shot prompting, in-context learning, and chain-of-thought reasoning. But there's a limitation. These models struggle when it comes to handling long-form information. They simply can't process information beyond a certain length, which is a problem for real-world applications that require long-term planning. One way to tackle this limitation is by increasing the input context length, similar to what GPT-3 did when it doubled its input length from 1K to 2K tokens as compared to GPT-2. But this isn't an ideal solution because it demands heavy computational power and still struggles with the issue of in-context dense attention. A recent alternative approach has been developing sparse attention to sidestep this problem, but it still needs a lot of computation and has to start from scratch. The memorizing transformer, or MEM-TRM, on the other hand, uses dense attention over both in-context tokens and memorized tokens. This allows it to handle up to 65K tokens and significantly improves its ability to handle long texts. However, it also has a limitation. As the model parameters are updated, the representations in memory may become outdated, affecting the overall effectiveness of memory augmentation. To address these issues, we propose a new framework called Language Models Augmented with Long-Term Memory, or LongMem. LongMem allows models to store previous context or knowledge into a non-differentiable memory bank. It uses a unique residual side network, or SideNet, which operates separately from the main memory module to prevent the issue of memory staleness. We extract attention keys and values from previous contexts using a frozen backbone LLM and store them in the memory bank. Then, the generated attention query of the current input is used to retrieve these cached keys and values from the memory, which are then integrated into learned hidden states through a joint attention mechanism. Additionally, we have designed cross-network residual connections between SideNet and the frozen backbone LLM for better knowledge transfer. Two main benefits emerge from our decoupled memory design. Firstly, it separates the process of encoding previous inputs into memory from the process of memory retrieval and fusion, thus resolving the issue of memory staleness. Secondly, adapting the entire LLM with memory augmentations is computationally inefficient and prone to catastrophic forgetting. As the backbone LLM is frozen during the memory-augmented adaptation stage, LongMem can effectively utilize pre-trained knowledge without the risk of catastrophic forgetting. We put LongMem to the test with two representative cases: language modeling with full-length book contexts, and in-context learning with thousands of task-relevant examples. The results show that our model consistently outperforms strong baselines in terms of long-text modeling and in-context learning abilities. Notably, LongMem improves LLM's long-context language modeling capabilities significantly and achieves state-of-the-art performance on a challenging long-context modeling benchmark. In-context learning improvements on popular NLU tasks were also notable when compared with MEM-TRM and other non-memory augmented baselines. Section Summary. Large language models, LLMs, have limitations in processing long-form information beyond a fixed context length. Scaling up the input context length incurs computation-intensive training, and the in-context dense attention is still heavily constrained by the quadratic computation complexity of transformer self-attention. To address this, the proposed framework for language models, Augmented with Long-Term Memory, LongMem, enables language models to cache long-form previous context or knowledge into the non-differentiable memory bank, and further take advantage of them via a decoupled memory module to address the memory staleness problem. LongMem outperforms strong baselines in terms of long text modeling and in-context learning abilities. Section 2 Methods. In this section, we explain how we can make large language models, LLMs, more efficient at using information from long-past contexts by introducing an additional memory module. Our method hinges on a new lightweight, adaptable component called a residual SideNet. This SideNet assists in blending the information from the memory context into the model. We will explain in detail how we integrate this memory augmentation into language modeling, how we use our SideNet to modify a pre-trained LLM to attend to both local and memory context, and how we manage the processes of encoding, storing, recalling, and integrating past memory for language modeling. First, let's talk about our model setup for language models equipped with long-term memory. The underlying structure for our model, called LongMem, is the well-known transformer architecture. It has three main elements: the static LLM, known as the frozen backbone, the SideNet, and the cache memory bank. In most pre-existing LLMs, the input has a fixed size, meaning they can only consider a specific portion of a longer sequence, for example, a book. This portion that fits within the size limit is referred to as the current input. Previous segments of the sequence that couldn't fit into the input are regarded as previous inputs and are used for memory augmentations. We use the frozen backbone LLM to encode both the current and previous inputs, but we extract different kinds of information from them. From the previous inputs, we take the key value pairs from the transformer's self-attention at a specific layer and store them in the cache memory bank. For the current inputs, we keep the hidden states from each decoder layer of the LLM and transfer these to the SideNet. The SideNet is trained to integrate the current input context with relevant cached previous contexts from the memory. The process starts with a forward pass through the frozen backbone LLM for a given fixed-sized input text sequence without any gradient calculation. The input sequence is first converted into an embedding space, outputting initial hidden states. Then, each subsequent layer of the LLM decoder uses the hidden states from the previous layer to compute new hidden states. When performing this forward pass for all previous inputs, the key value pairs used for self-attention at a certain decoder layer are stored in the cache memory bank. This memory bank maintains the latest key value pairs from the previous inputs and is used as memory augmentations for future inputs. Once the memory retrieval and fusion process is complete, the memory bank removes the key value pairs of the oldest sequences and appends the current sequences to the cached vector bank. This method ensures causality in language modeling at the sequence level and allows the memory bank to always keep records of the nearest previous context for the current inputs. Next, the SideNet module takes the hidden states from the current input and passed key value pairs from the cache memory bank to compute memory-augmented representations. Our SideNet is composed of several standard transformer decoder layers, with one special memory-augmented decoder layer. This memory-augmented layer takes a memory-augmented input, including the top relevant key value pairs in memory and the hidden states from the current input. The key value pairs are retrieved using a token-based memory retrieval module. The SideNet then computes the output using the memory-augmented input. Finally, the probability for each token is calculated using the last hidden states from the SideNet. The aim is to maximize the likelihood of the next token based on the preceding context. This output embedding is shared by both the frozen LLM and the SideNet. We apply a memory-augmented training adaptation for LongMem to make the best use of the separate memory. The goal is to maximize the likelihood of the next token based on the previous context, which is a standard approach in language modeling. This method forms the basis for unsupervised pre-training, and the text corpus used for pre-training is randomly sampled. Section Summary. The proposed LongMem model augments a frozen backbone LLM with a decoupled memory module to enable the LLM to retrieve relevant information from past long context in memory. The SideNet module is designed to fuse the memory context information and is continually trained in an efficient way. The LongMem model consists of three key components: the frozen backbone LLM, SideNet, and cache memory bank. Section 2.2 Residual SideNet. Our approach involves creating a new network we call SideNet, which is based on the well-established transformer architecture. To establish a balance between complexity and performance, we employ a reduction factor to determine the number of decoder layers in SideNet. If the original model, which we call the Backbone Language Learning Model, LLM, has a number of layers denoted as L, the number of decoder layers in SideNet, denoted as L, is simply half of that, i.e., L equals 2L. This assumes a reduction factor of 2. To kickstart the learning process of SideNet, we use the weight values of the corresponding layers from the pre-trained backbone LLM. Thus, each decoder layer in SideNet gets a head start by using the same depth weight values from the backbone LLM. The SideNet's operational flow begins with taking the output from the embedding layer of the backbone LLM. Additionally, it also reuses the language modeling layer from the backbone LLM, which remains unchanged during the continual adaptation phase. The rest of the parameters in SideNet are adjusted during the memory-augmented adaptation stage based on the training signals received. As a result, SideNet, while being lightweight, can learn quickly by leveraging the knowledge transferred from the pre-trained parameters. We enhance the learning capacity of SideNet through a technique we call cross-network residual connections. In this process, we blend representations from the backbone LLM into SideNet. More specifically, we calculate the difference between the output hidden states at the 2LTH and 2L2TH layers of the backbone LLM and add it to the output hidden states at the LTH layer of SideNet. The resultant sum then serves as the input to the subsequent L+1TH layer of SideNet. To clarify this, consider the following scenario. The input to the next layer of SideNet, denoted as L+1, is computed as the sum of the original hidden state processed through the previous layer and the calculated difference of the hidden states from the backbone LLM. It's important to highlight that the established practices for residual connections in the decoder layer of a transformer model remain in place and work in parallel with our proposed cross-network residual connections. Section Summary. The SideNet architecture is implemented based on transformer, with the number of decoder layers equal to the number of layers in the backbone LLM divided by a reduction factor. The weights of each decoder layer in SideNet are initialized from the corresponding pre-trained decoder layer of the backbone LLM with the same depth. Cross-network residual connections are proposed to fuse representations from the backbone LLM into SideNet, which involves adding the difference between output hidden states at certain layers of the backbone LLM as the residual connections to the output hidden states at certain layers of SideNet. Section 2.3 Memory Retrieval and Fusion. In Section 2.3, we discuss memory retrieval and fusion, a key part of our model called LongMem. This module allows LongMem to access long-term memory, and it is made up of two components: token-to-chunk memory retrieval and memory fusion. Let's talk about the first part, token-to-chunk memory retrieval. Instead of trying to link each individual word, or token, with another token, our approach links a token to a larger piece of text, a chunk. This chunk is an n-gram structure, meaning it's a group of contiguous tokens of a certain size, which we call CSZ. We keep a memory bank, which holds key value pairs representing these chunks of tokens. We split this bank into a certain number of chunks, based on the size of these chunks, CSZ. By pooling together the vectors of each chunk, we get the key vector we need for retrieval. We then retrieve a number of key value chunks, which corresponds to the top results from a dot product operation between the attention query of the current input token and the mean pooled attention key of a potential chunk. After retrieval, we process the chunks into a flat structure of key value pairs at the token level. By shifting from token to token to chunk retrieval, we streamline the process and improve its speed. We've also noticed an increase in the retrieval accuracy. The chunk size, CSZ, can be tweaked depending on the downstream tasks. For instance, when learning in context, finer detail is required, and therefore, a smaller CSZ is beneficial. Next, we have memory fusion, which happens within a special layer that's enhanced with memory capabilities. This layer extends the traditional transformer decoder layer's multi-head self-attention to a joint attention mechanism. This allows each token to focus on both local contexts and the contexts retrieved from memory. In this layer, we take the output from the previous layer and the retrieved attention key value pairs, and we generate the hidden state for the current memory enhanced layer. This process involves a series of operations, including calculating the softmax function and a concatenation operation to form intermediate variables, which are then used to compute the output hidden state. The process also involves a trainable gating vector, which plays a role in determining the contribution from local and global contexts. Notably, each token has a unique set of retrieved attention key value pairs from the cached memory. This uniqueness ensures that our model can tailor its understanding to each specific token. We use specific matrices to transform the output from the previous layer into queries, keys, and values for the current layer's attention mechanism. Section Summary. The LongMem model achieves long-term memory via a memory augmentation module for retrieval and fusion. Token-to-chunk retrieval is used instead of token-to-token retrieval, which reduces the size of the retrieval index and accelerates the process while improving retrieval accuracy. Memory fusion is performed within a special memory-augmented layer, which enables each token to attend on both local contexts and retrieved memory contexts. Section 3 Experiments. In our third section, we test our LongMem model, focusing on tasks that require in-memory long contexts. We're particularly interested in seeing how it performs with long text language modeling and understanding, and how it learns with infinite-length contexts when we load a high number of examples into cached memory. Now, let's talk about how we set up the training. We typically prepare or batchify large datasets by cutting them into equal-length text segments and shuffling these pieces to create mini-batches. With LongMem, however, we need to maintain the sequence order, so we do things a little differently. We divide all long documents into equivalent length groups and then shuffle these documents within each group. Then, we join these shuffled documents and cut them into ordered segments. To make sure that two consecutive segments from the same document end up in two consecutive input batches, we pick one segment from each document group with the same position within its group. Thus, a mini-batch is made up of segments from the same number of document groups. As we go through the training steps, the attention key value pairs in the memory bank perfectly match the previous context of current inputs within the same document. In terms of the training corpus and hyperparameters, we use a subset of the pile, which includes various data sources like Book Corpus 2, Books 3, Open Web Text 2, Stack Exchange, Wikipedia, Gutenberg, PG19, NIH Exporter, and PILE-CC datasets. We use a version of GPT-2, with 407 million parameters, as the pre-trained backbone language model, LLM. We had to make a slight adjustment to the position embedding because the original GPT-2 model didn't perform well when trying to learn long-distance dependencies. Our LLM has an architecture with 24 layers, 16 heads, and a model size of 64. The SideNet, which assists our LLM, has an architecture with 12 layers, 16 heads, and a model size of 64. We use a batch size of 256 and a sequence length of 1024 for our training, which covers 26 billion tokens. Each chunk contains 4 tokens and the memory holds 65,000 key value pairs of tokens. We fetch 64 attention key value pairs per token for augmentation, which equates to 16 text chunks. The 9th layer of SideNet serves as the memory augmentation layer, and the attention keys and values from the 18th layer of the backbone LLM are stored for future use. For memory retrieval, each GPU can build and update their own memory retrieval module, which holds 65,536 key value pairs of tokens. We've also employed the Phase toolkit to build an exact search index for efficient token retrieval. This approach allows us to quickly find the relevant data in the memory, taking about 15 milliseconds per 1,000 tokens, about 55% of the time it takes for the LLM's forward pass. As for our baseline comparisons, we're looking at the pre-trained GPT-2 and the memorizing transformer, MEM-TRM. The latter is another memory-augmented model that we've adjusted to use external memory. We use the same settings for both baselines as we do for our own model to ensure fair comparison. Section Summary. The LongMem model is evaluated on long context tasks such as long text language modeling and infinite length in context learning. The training setup involves dividing long documents into batches and shuffling them within each group to ensure global causality at the segment level. The memory retrieval module uses the Phase toolkit to construct an exact search index on GPU for efficient retrieval. Section 3.2 Long Context Language Modeling. Section 3.2 of the paper discusses long context language modeling and how it can gain considerable advantage from the enhanced decoupled memory of past long contexts. This kind of memory storage can come in handy when dealing with large bodies of text, like novels, as the stored information can help models better understand and generate subsequent parts of the story based on what they've learned from previous context and character relationships. The researchers evaluated their model, LongMem, and compared it to other existing models on 3 long context modeling datasets: Project Gutenberg 2020 to 2022, Archive, and Chapter Break. They primarily included books and papers that were at least 16,000 words long. They used a zero-shot approach for the evaluations, meaning no task-specific tuning was done. The first dataset they used was the Project Gutenberg 2020 to 2022 language modeling dataset, a collection of books published between 2020 and 2022, which they referred to as PG22. The PG22 dataset was distinct from their training subset, PG19, in both domains and writing styles, given that the latter includes books published prior to 1919. They divided this dataset based on length range for different validation splits. The second dataset, the Archive dataset, was composed of papers related to mathematics, computer science, and physics. The selected subset of papers were not used during their training phase and thus represent out-of-distribution data. They reported the language modeling complexity level, or perplexity, for both the PG22 and Archive datasets. The third dataset, Chapter Break, is a unique benchmark that requires models to identify the beginning of a new chapter from a set of challenging negative segments, all sampled from the same book. This is done by taking into account the long context of previous chapters. Despite being a challenge even for state-of-the-art transformers, they included a subset of Chapter Break, the archive of our own, AO3, that contains fanfiction pieces. This dataset was divided into 8 sections based on the length of the prefix, ranging from 500 to 8,000 tokens. For their evaluations, they measured the difficulty of each candidate segment using a metric called perplexity, and the one with the lowest perplexity was marked as the correct label. The accuracy of the model in identifying the correct suffix was the primary evaluation metric. The results showed that LongMem significantly outperformed all considered models in these long text language modeling datasets, improving perplexity by 1.38 to 1.62 points on different length splits of PG22, and by 1.0 points on the Archive dataset. Notably, LongMem achieved an impressive 40.5% accuracy rate on the AO3 suffix identification benchmark, outdoing even powerful long context transformers and the most recent long-length language models like GPT-3, which boasts 313 times larger parameters. This notable improvement on these datasets shows that LongMem is quite adept at understanding past long context stored in cached memory and successfully applying this understanding to future inputs in language modeling. Section Summary. The LongMem model significantly outperforms all considered baselines on long text language modeling datasets, with improvements of -1.38 to -1.62 perplexity on different length splits of PG22 and -1.0 ppl on archive datasets. Additionally, the proposed method achieves the state-of-the-art performance of 40.5% accuracy on chapter break, text normal, AO3. Suffix identification benchmark and outperforms both the strong long context transformers and latest LLM GPT-3 with 313x larger parameters. These results demonstrate that LongMem can comprehend past long context in cached memory to well complete the language modeling towards future inputs. Section 3.3 Memory-Augmented in Context Learning. Large language models, LLMs, have shown promising results in the area of in-context learning, ICL, which involves learning from a few select examples in a given context. However, traditional ICL approaches are significantly constrained by the length of the input context, limiting the amount of supervision that can be gathered from demonstration examples within the training set. To address this, we've developed a method we call LongMem, which uses an unlimited length memory augmentation. This technique allows us to move beyond the number of demonstration examples in the local context. With LongMem, we can even take into consideration the entire training set by loading it into what we call the cached memory. In doing so, LongMem extends the possibilities of traditional few-shot in-context learning, enabling memory-augmented in-context learning with thousands of supporting demonstration examples. To evaluate LongMem, we compared it with the baseline models across 5 natural language understanding (NLU) datasets: SST2, MPQA, MR, SubJ, and SST5. We assessed the models in 2 scenarios, one with only 4 demonstration examples, 4-shot, and the other with 20-shot. In the 4-shot scenario, data is relatively scarce, whereas in the 20-shot scenario, the length of input can almost reach 1K, providing plenty of context for self-supervision. We converted the K-shot examples into semantically meaningful demonstration examples using a fixed text template. The template takes the form, review, X sentiment, Y, for each, X, Y. Pair in the training set for sentiment analysis tasks. We also evaluated 3-shot ICL on question answering tasks of squad in an open-ended generation setting. The demonstration examples were separated by new lines, and the predicted label was generated using greedy decoding based on the demonstration examples and test cases in context. We use prediction accuracy as our evaluation metric, reporting the mean and standard deviation across 6 runs with different random seeds to account for the randomness in selecting K-shot demonstration examples. As the size of the text chunks retrieved can impact the performance, we fine-tuned this chunk size on the validation set of SST2. We found the optimal chunk size to be 2, which was used to report the results for MEM-TRM in our model. The results showed LongMem significantly improved performance across all NLU tasks in the 20-shot scenario, achieving an average score increase of +8.0 over pre-trained GPT-2 and MEM-TRM. LongMem also enhanced performance in the 4-shot scenario. Furthermore, LongMem improved the in-context learning capabilities of LLMs on open-ended generation tasks, achieving a +4.5 exact match M score increase on squad. These results suggest that the demonstration examples stored in the cached memory can be viewed as auxiliary contextual demonstrations, aiding in context learning. LongMem can utilize the task-relevant knowledge from both local contextual demonstrations and in-memory augmented demonstrations for improved in-context learning. Section Summary. The LongMem method proposes unlimited length memory augmentation to overcome the limitation of the number of demonstration examples in the local context, allowing for memory-augmented in-context learning with thousands of auxiliary demonstration examples. The proposed model achieves remarkable improvements on all NLU tasks in 20-shot sufficient in-context setting, with +8.0 average scores increase over pre-trained GPT-2 and MEM-TRM, and also improves the in-context learning capabilities of LLMs on open-ended generation tasks, with +4.5 M score increase on squad. Section 3.4 Ablation Studies. We've been able to confirm, through our research, that our system, LongMem, is particularly effective at handling long context models, understanding long contexts, and in-context learning with a multitude of examples. However, we're aware that the configuration of the memory bank, specifically parameters like memory size, referred to as MSZ, and chunk size, referred to as CSZ, play a crucial role in how well our system performs. To better understand these factors, we ran several ablation studies examining the impact of different memory sizes and chunk sizes on our system's performance. Let's talk about chunk size first. Chunk size, or CSZ, determines how precise the memory retrieval can be. This means that tasks requiring detailed, specific retrieval, such as in context learning, might be affected by the chunk size we choose. To understand this, we conducted a study with chunk sizes of 2, 4, and 8 units. Interestingly, a chunk size of 2 units performed the best on in-context learning tasks across 5 different natural language understanding (NLU) datasets. This result fits with the nature of NLU tasks, which often need to retrieve and combine very specific pieces of information for accurate classification. Next, let's explore the effects of memory size, or MSZ. Memory size essentially sets the limit for the memory bank storage capacity. It should ideally be chosen in accordance with the average length of the documents or contexts being processed. For instance, if we're dealing with books averaging 16,000 tokens, it would be logical to set the memory size to 16,000 tokens. However, when we're dealing with tasks like chapter break, a memory size of 65,000 tokens can be overkill, as the full prefix context length doesn't exceed 65,000 tokens. We further studied the effects of memory sizes of 8,000, 16,000, 32,000, and 65,000 tokens during the inference stage on the PG22 language modeling datasets. The results indicated that the best performance came from a memory size of 16,000 tokens, which aligns well with the average length of the books we were modeling, with lengths ranging from 8,000 to 50,000 tokens. So, in summary, our ablation studies show that optimizing parameters like chunk size and memory size can make a significant difference in our system's performance. Our findings indicate that smaller chunk sizes work best for fine-grained tasks, while memory size should be aligned with the average length of the documents or contexts being handled. Section summary. The effectiveness of LongMem in utilizing cached memory for long context modeling, long context understanding, and many-shot in context learning has been empirically verified. A series of ablation studies were performed to evaluate the effects of hyperparameters like memory size and chunk size on task performance. The results showed that a chunk size of 2 yielded the best performance on in-context learning tasks, while a memory size of 16K was the most effective for modeling books with an average length of 8K/50K. Section 4. Related work. In this section, we discuss the related works and developments in our field that influenced our study. Let's begin by examining large language models, or LLMs for short. LLMs, including GPT-2, GPT-3, Opt, and Bloom, have been real game changers in natural language processing, driving advances in language comprehension, language generation, and even in tasks that combine vision and language. Furthermore, these models show remarkable abilities when we increase their size, such as the capacity to learn from a few examples within a specific context, engage in multi-step reasoning, and autocomplete code, among other things. Now, let's move on to the area of X-formers. These are variants of transformers designed to handle long-range contexts. A strategy employed by Transformer XL is to store and reuse the attention keys and values from past segments in a recurrent fashion. More recent X-formers, such as linformer, longformer, and routing transformer, have proposed various sparse attention methods to reduce their computational complexity from a square of the length of the sequence to its logarithm or even linear time complexity. Big Bird, another variant, can manage sequences up to 4,000 tokens long by only attending to a subset of context tokens. However, while these X-formers provide considerable improvements in efficiency, their gains are not as impressive when dealing with sequences that span the length of a book. Also, the maximum sequence length of these methods is capped at 16,000 tokens, which is inadequate for modeling longer sequences, such as full-length books or Wikipedia pages, which on average contain about 70,000 tokens in the PG19 dataset. Lastly, we'll examine side tuning. This method employs a lightweight side network that is trained specifically for the task at hand and combined with a fixed pre-trained network. We've incorporated the use of a side network in our method, but we've made some modifications to the learning objective and the way it's integrated with the main network. Another related work, LongMem, proposes to equip LLMs with a separate memory to remember long-past inputs, which doesn't require any task-specific tuning. This approach introduces a new concept of cross-network residual connections, which is a different method of integration compared to the simple summation used in side tuning. Section summary. Large language models, LLMs, like GPT-2, GPT-3, Opt, and Bloom have revolutionized NLP research and exhibit emergent abilities, like few-shot in context learning and multi-step reasoning. X-formers, such as Transformer XL, longformer, and routing transformer, propose various sparse attention mechanisms to decrease complexity, but their efficiency gains are not remarkable for modeling book-level length sequences. Side tuning is a task-specific tuning method for pre-trained models, while LongMem proposes to augment LLMs with decoupled memory for memorizing long-passed inputs without task-specific tuning.